Good morning, everyone. I welcome you in this another session of power system analysis. Today, we are going to discuss about the fault analysis. We are going to discuss the fundamental considerations for the fault analysis. So, basically, we are going to study about the fundamental considerations for the fault analysis. So far, we have seen that the steady state behavior of power system under normal operating conditions and its dynamic behavior under the small scale perturbations. Now, in this lecture, it has been totally devoted to the abnormal system and behavior under conditions of symmetrical short circuits. Now, these such conditions are caused in system accidentally through insulation failure of equipments or flashover of lines initiated by a lightning stroke or through accidental faulty operations. The system, which must be protected against the flow of heavy short circuit currents, which can cause the permanent damage also to the major of equipments connected in the power system network. So, by disconnecting the faulty part of the system using the circuit breakers operated by protecting relays, we can achieve this system protections. Now, for the proper choice of circuit breakers and protective relays, we must estimate the magnitude of currents that would flow under the short circuit conditions. And this is why we do the fault analysis or we study the fault analysis. It is very important that the majority of the system faults are not three-phase faults, but faults involving one line to ground faults or occasionally two line to ground faults. These are unsymmetrical faults requiring special tools like symmetrical components and form the subject of study of the next upcoming slides and the sessions. Through the symmetrical faults, the rare they are rare and the symmetrical fault analysis which must be carried out as this type of fault generally leads to most severe fault current flowing against which the system must be protected. So the symmetrical fault analysis is of course simpler to carry out. It is important to note down that the symmetrical faults may be a solid three-phase short circuit or it may involve the arc impedance. Now, the power network comprises synchronous generator, transformers, lines, and the loads. Now we know that through the operating conditions at the time of fault are important, the loads can be neglected during the fault as a voltage dip very low so that current drawn by the loads can be neglected in comparison to fault currents. The synchronous generator during the short circuit has a characteristic time varying behavior. In the event of short circuit, the flux per pole undergoes dynamic change with associated transients in the damper and field windings. The reactance of the circuit model of the machine changes in the first few cycles from low sub-transient reactance to a higher transient values, and finally settling at a still higher synchronous, or we can say steady state values. Depending on the arcing or the arc interruptions time of the circuit breakers, a suitable reactance value is used for the circuit model to synchronous generator for short circuit analysis. Now, in a modern power system where a large interconnection is being done, is there, heavy current flows during the fault must be interrupted before the steady state conditions are established. Now, we can also say furthermore, from the consideration of mechanical forces that act on circuit breaker components, the maximum current that a breaker has to carry momentarily must also be determined. Therefore, we can say that for selecting a circuit breaker, we must determine the initial current that flows on occurrence of the short circuit and also the current in the transients that flows at the time of circuit interruptions. The electrical systems occasionally experiences the short circuit, and this results in abnormally high currents. Now, overcurrent protective devices should isolate faults at a given location safely with minimum damage. Now, the parts of the system shall be able to withstand the resulting mechanical and thermal stress as well. And the magnitudes of the fault currents are usually estimated by the calculations. The equipment is selected using the calculation results. Now, how it has been done? Is it a hand? It is a tedious hand calculations? No, it's not. For a large power system networks, we use the programs, the computational techniques to solve the fault analysis or to do the short circuit analysis. Not only limited to the programs, but we have several softwares or the simulation programs where we can simulate the complete network of the system or a part of a network of a system for the short circuit analysis, which gives you the results of the short circuit, either the subtransient short circuit current, transient short circuit current, and the steady state currents. The softwares will be able to provide the complete information about the various short circuit studies. Such software is one of the such software is ETAP. There are other several softwares like MATLAB or MI Power or Big Silent Power Factory. So all these softwares are very useful and are presently used in industries, in the power system industry, for all the calculations and coordinations of relay coordinations, for load analysis, for short circuit analysis, for DC transient analysis, for transient analysis, for arc flash analysis, and many more. There are a lot of facilities being available in these softwares. Now, what are the sources of fault current? The very first source is the synchronous generators, synchronous motors and condensers, induction machines, electrical utility systems, distributed generations, representation of rotating machines. Now look at this. This is a representation of a rotating machine where E is the induced EMF and XD double dash, XD dash, and XS are the reactances at the various time intervals. The XT double dash is the reactance at the subtransient interval, XD dash is the reactance at the transient interval, and XS is the steady state reactance. So the values of these sub-transient reactance, and steady state reactances also varies with respect to time period. And as these values are changing, your fault level is also different at each interval. The fault current is different at each interval. So this is the magnetic field in the machine decays. Now the transmission line fault analysis. The cause of electric power system fault is insulation breakdown or the insulation compromises. Now this breakdown can be due to the variety of different factors. Lightning the ionizing air, wires blowing together in the wind, animals or plants coming in contact with the wires, the salt spray or the pollution on insulators. For an example, we are having the lightning ionizes the air, and when the air gets ionized, the conductivity between the two near adjacent conductors increased, or even from the conductor to the nearby trees or the plants increased. The electric strength is reduced in that condition. And once the conducting medium is being created, the current can pass through these medium and create a short circuits. The another reason is the wire blowing together in the wind. When we do not have the appropriate sags and the distance between the two conductors, and when the heavy wind blows, these conductors, the adjacent conductors, get tangled or may get come in contact with each other and may cause a short circuit. Another reason is during the rainy seasons or in the storms, we know that due to the heavy wind flows, the falls get the trees get falls on these transmission lines or on the conductors, or also sometimes the mishappenings occur to the animals which may get come in contact with these conductors. So such unfortunate things can also cause the short circuits in the system. So the pollution depositions on the or the salt sprays depositions over the conductor also causes the short circuit conditions. Now there are two main types of faults. The very first fault is the symmetric faults. The system in the symmetrical faults, the system remains balanced. These faults are relatively rare but are the easiest to analyze, so we will consider them first. The very second type of fault is that unsymmetrical faults. And system is no longer balanced. Very common, but more difficult to analyze in this case. Because first of all, what we have to do? We have to make the unbalanced systems into a balanced system. And then only we will be able to do the analysis of this. The most common type of fault on these are the three-phase systems. By far is a single line to ground fault, followed by the line-to-line faults and double line to ground faults. And then in the last, the rarest occurrence is of the balanced three-phase faults. Now, the lightning strike event sequence, what happens, that how these creates the fault. So when a lightning hits the line, it is setting up the ionized path to the ground. It has been estimated that 30 million lightning strikes per year happen in United States, and it is and it is one of the most uh, highest occurrence rate of lightning strikes in the United States. The single typical stroke might have 25,000 amperes with a with a rise time of 10 microseconds, which can dissipate in 20 microseconds. Now, multiple strokes can occur in a single flash, causing the lightning to appear to flicker, with a total event lasting up to a second. The conduction path is maintained by ionized air after lightning stroke energy has dissipated. Now, within one or two cycles, that is within the 16 milliseconds, the relays at both the ends of the line detect the high currents and signals the circuit breaker to open the line. These circuit breakers open the line which are located nearer by to the locations see the decreased voltages. We know that the short circuits are the low voltage phenomena, the faults are the low voltage phenomena. So the voltage get reduced in those conditions. And the circuit breaker open to de-energize the line in an additional 1 or 2 seconds. In this, the breaking the tens of thousands of amperes of fault current is no small feat. With the line removed, voltages usually return to the normal value, and the circuit breaker may reclose after several seconds, trying to restore the faulted lines of service. Now, if it doesn't happen, then it will again open up and then again will reclose. So this until and unless the fault is completely been eradicated from the line and the system is being restored. Under the steady state short circuit conditions, usually the armature reaction of a synchronous generator produces a demagnetizing flux. In terms of circuit, this effect is modeled as a reactance XA in series with the induced rate. The fault current causes the equipment damage due to the both thermal and mechanical processes. Goal of fault analysis is to determine the magnitudes of the current present during a fault and need to determine the maximum current to ensure devices can survive the fault. It is also important to determine the maximum current the circuit breakers need to interrupt to correctly size the circuit breakers. That means we have to identify the size of the circuit breakers, the ratings of the circuit breakers correctly so that it can interrupt the maximum current that may happen during the short circuit conditions. Now let's do the RLC circuit analysis for this thing. Let us consider the short circuit transient on transmission line. Now there are certain simplifying assumptions that are important to made at this stage. The very first assumption is that the line is fed from a constant voltage source. That means the voltage is magnitude is constant. The second assumption is the short circuit takes place when the line is unloaded. In case the short circuit of the loaded line happens, that will be we will discuss it later. But before we are assuming that the unloaded synchronous machine is being done and there is a short circuit. The line capacitance is negligible and the line can be represented by a lumped RL series circuit. Now with the above assumptions, with these assumptions, the line can be represented by a circuit model as shown in this figure. The short circuit is assumed to take place at t is equal to 0, and this voltage is been given by root 2 V cos of omega t plus alpha. Now the parameter alpha controls the instant of the voltage wave when the short circuit occurs. It is known from the circuit theory that the current after the short circuit is composed of two parts. That is the transient and the steadies. That means the current will have the two components, that is the steady state value and the transient value. The steady state component from the standard phasor is been given by root 2 V cos of omega t plus alpha minus theta z upon z. The steady state phasor magnitude is IAC, which is equal to V by Z in the phasor values, where Z is equal to under root of R square plus omega L square, which is equal to R square plus X square, and the current phasor angle is minus theta z. Now this theta z is the impedance angle, and it can be measured as tan inverse of omega upon R or X upon R. The corresponding instantaneous current then it would be IAC will be equal to root 2 V cos omega t plus alpha minus theta z upon C. The second is the exponentially decaying DC current component, which is your transient value. Now this IDC is given by C1 e to the power minus t upon t, where t is the time constant. It can be equal to L upon R, the inductance of the circuit upon the resistance of the circuit. And the value of C1 is determined from the initial conditions. By substituting the t is equal to 0, we will be finding out the values for the current. Now, when you substitute this value t is equal to 0, we will be getting that C1 is equal to root 2 V upon Z cos of alpha minus theta z, which depends on alpha. Where I've told you that alpha will decide that the value of instant value of the voltage. Now there are two terms. Consider this one, that one at the starting we are having here we are having some exponentially decaying component. This is your exponentially decaying component. After some time period, it gets equal. Now the superposition of steady state component and the exponentially decaying of DC offset current. Hence, IT is a sinusoidal superimposed on a decaying DC current. The magnitude of IDC at t is equal to 0 depends on when the switch is closed. For the fault analysis, we are just concerned with the worst case. The highest DC current occurs for alpha is equal to theta z minus pi, where C1 is equal to root 2V upon Z. I will substitute these values of alpha and C1 in the instantaneous current equation where IAC and IDC are the two components. The IT will be equal to root 2V upon Z minus of cos of omega t plus e to the power minus t upon t. Now this first term is your symmetrical short circuit current, and the second term is your DC offset current. The interrupting capability of a circuit breaker is specified in terms of RMS current. It can interrupt. The function IT is equal to root 2V upon Z minus of cos of omega t plus e to the power minus t upon t is not periodic. So we cannot formally define an RMS value. However, if t so now for the selection of the circuit breakers, the momentary short circuit current is taken consideration to its maximum possible value. That is to a safe choice. It's a safe choice to select it for the measurement. Now there is one another question arises in the mind that what is the current to be interrupted? As has been pointed out earlier also, that the modern day circuit breakers are designed to interrupt the current in the first few cycles. It means that when the current is interrupted, the DC offset has not yet died out and so contributes to the current to be interrupted. Rather than computing the value of DC offset at the time of interruption, the symmetrical short circuit current alone is calculated. So this shows that the increased by an empirical multiplying factor to account for the DC offset current. Now this RMS value is a function which has a maximum value of root 3 IAC, and therefore the worst effect of the DC current component is included simply by multiplying the AC fault currents by root 3. Now look at this generator modeling for during the faults. Now it is important that under the steady state short circuit conditions, the armature reaction of synchronous generator produces a demagnetizing effect or flux. Now in terms of circuit, this effect is modeled as a reactance XA in series with the induced EMF. This reactance, when combined with the leakage reactance XL of the machine, is called as the synchronous reactance XT, which is nothing but XD is your direct axis synchronous reactance in case of salient pole machines. The armature resistance being small, which can be neglected. The steady state short circuit model of a synchronous machine on a per phase basis has been shown to you in this figure. Now, during the fault, only the devices that can contribute the fault current are those with the energy storage. Thus, the models of the generators are very important since they contribute the bulk of the fault currents. The generators can be approximated as a constant voltage behind a time varying reactance. Now, this time varying reactance is typically approximated using the three different values. The direct axis subtransient reactance xd double dash, direct axis transient reactance xd dash, and the direct axis synchronous reactance xd. We then estimate the currents using the circuit theory. For example, we could calculate the steady state current that would occur after a three-phase short circuit if no circuit breakers interrupt the current. Now consider a sudden short circuit, a three-phase fault on a synchronous generator which is initially operating under the open circuit conditions, and the machine undergoes a transient in all the three phases, finally ending up in the steady state conditions. The machine undergoes, or we can say the circuit breaker must of course interrupt the current much before the steady state conditions are reached, and immediately upon the short circuit the DC offset current appears in all the three phases, each with a different magnitude. Since the point of the voltage wave at which the short circuit occurs is different for each phase. Now these DC offset currents are responsible, or we can say the accounted for separately on an empirical base. That is, therefore, for the short circuit studies, we must or we need to concentrate our attention on symmetrical short circuit currents only. And immediately in the event of the short circuit, the symmetrical short circuit current is limited only by a leakage reactance of the machine. Now, for a balanced three-phase fault on a generator, the terminals AC fault current is being shown to you. Since the air gap flux cannot change instantaneously, to counter the demagnetization of the armature short circuit current, the currents appear in the field winding as well as in the damper winding in direction to help the main flux. Now, these current decays in accordance with the winding time constant. Now, the time constant of the damper windings, which has low leakage inductance, is much less than that of the field winding, which has higher leakage inductance. Thus, during the initial part of the short circuit, the damper and the field windings have transformer currents induced in them so that in the circuit model, the reactance XF of field winding and XDW of the damper winding appears in parallel with XA. Now, as the damper winding currents are first to die out, the XDW effectively becomes open circuit, and at the later stage, the XF become open circuit. The machine reactance thus changes from parallel combinations of XA, XF, and XDW during the initial period of the short circuit to XA and XF in parallel in the middle period of the short circuit, and finally it comes to XA in the steady state condition, the steady state period. PD double dash is a direct axis transient time constant which is approximately equal to 0.035 seconds, and TD dash is a direct axis time constant, direct axis transient time constant which nearby is equal to approximately equal to 1 second. Now this phasor current is then written as by this given equation, and the maximum DC offset current can be calculated by this, where EA is the armature time constant which is approximately equal to 0.2 seconds. Now look at these conditions. These are the short circuit currents which have been defined in the various conditions. This is a sub-transient component where your sub-transient reactance is being considered. Now, since when due to the sub-transient period, the reactances are connected in parallel, so the least value of the reactance net will be there, and due to which the current will be maximum, and this can be reflected in this sub-transient period. Now, after the middle period of the transient condition, the reactance is reduced. Sorry, the reactance is increased by removal of the damper winding effects in the middle period, and it causes the current to decrease during the transient components. And in the last stage, the effect of field winding is also being neglected and is treated as the open circuited condition. That in that case, the reactance will be the maximum, and the steady state condition will be achieved during the steady state period. So if you examine the oscillograph shown in this, the short circuit current of a synchronous machine after the DC offset current has been removed from it, you will find that the current wave shape in this. The envelope of the current wave shape is being shown in this, and the short circuit current can be divided into three periods: initial sub-transient period, when the current is large as the machine offers the sub-transient reactance, and the middle transient period where the machine offers the transient reactance, and finally the steady state period when the machine offers the synchronous reactance. If the transient envelope is extrapolated backward in time period, the difference between the transient and the sub-transient envelopes can be is the current. That is your delta I dash dash. Okay, so the difference in this, if I extrapolate it, then the difference in the current will be your delta I double dash, corresponding to the damper winding current, which decays fast according to the damper winding time constant. Now, similarly, the difference delta I dash, if I extrapolate this steady state, then I will be getting this delta I dash between the steady state period and the transient envelope, and decays in accordance with the field time constant. So this is what we were discussing about the short circuit currents in when the synchronous machine undergoes a three-phase balance fault when it is unloaded, when there is no loaded, when the machine is not loaded.
In the next session, we will discuss about the line-to-line faults. The very first question is said that a single line to ground fault occurs on a three-phase isolated neutral system with a line to neutral voltage of VkV. The potentials on a healthy phases rise to a value equal to root 2 V volts kV, root 2 VkV, sorry 3 VkV or 1 by root 3 kV. Okay. Next question is that if all the sequence voltages at the fault point in a power system are equal, then the fault is what? This is very simple. If all the sequence voltages of the fault point in a power system are equal, then a fault is what? Is it symmetrical or unsymmetrical? Try to solve it. I've given you the hint. Then the zero sequence current of a generator for a line to ground fault, that is for the single line to ground fault, is been given to you. The current through the neutral during the fault will be what? Just in the previous slide, we have discussed this thing. So you can solve it very easily. Try to solve it. We will discuss it in the next session. The fourth question says the severity of a line to ground and the three-phase faults at the terminal of an unloaded synchronous generator is to be same. If the terminal voltage is given, that is 1 per unit, that is Z1 and impedance is the positive and negative impedances are also given, which are equal to 0.1 per unit, and the zero sequence impedance is also given, that is J 0.05 for an alternator. Then the required inductive reactance for neutral grounding is what? This is very simple. You just need to clarify for the two of the cases. Okay, this question is very simple. You just need to focus on one point, that is you have to find out the equation for the line to ground fault and equation for the three phase faults. Okay, once you have the equations, you can easily identify then what will be the x2, that is the xn we can say. Okay, or we can say the zn has to be calculated. Is this clear? I have given you the hint. You try to solve it out. The most frequently occurring fault in the power system is what? The most frequently occurring faults. Remember this thing, that most of the faults occur frequently in the distribution systems. And in the distribution systems, the fault occur due to the short circuit between the two transmission lines, due to the falling of the trees, due to the birds, or due to the rainy seasons and various other factors, due to the breaking of the line, breakage of the line conductor and various others. So the most of the faults occur in the distribution side, and they are maximum category is the line to ground fault. So correct answer is line to ground fault. In the sixth question, it has been said in which type of the faults all the three phase components IA, IA0, IA1 and IA2 are equal, and IA0. All or these are equal. In which type of faults? The currents are equal. It is none other than the line to ground fault. Now, when a line to ground fault occurs, the current in the faulted phase is 100 amperes. The zero sequence circuit current in this case will be what? The line to ground fault current is given. The zero sequence current has been asked. It is very easy. It is very equal. That is your IA naught is equal to what? Remember the equation which I have told you. It is with terms of 3. Okay. It is what equal to? It is equal to IF upon 3. Okay. Now, in the eighth question, in which type of fault positive sequence and negative sequence voltages are equal? This we will discuss it later, next section, when we will discuss about the line-to-line faults. Now, for the fault analysis in power system, the symmetrical components are used because the results are required in terms of symmetrical components. Not necessary. Not necessary. Sequence network do not have mutual coupling. Not necessary. Number of equations becomes smaller. It's also not necessary, and all of those. Results are required. We do not require the results to be in symmetrical components. So yes, it is the yes, but it makes the easy calculations to get the results in symmetrical components. We will discuss it. I'm leaving it up to you. Choose the correct one from the given statement. There is a minimum sequence voltage and maximum negative sequence voltages at fault point. Zero and negative sequence voltage is at maximum at fault point towards the neutral. The zero sequence and negative sequence voltages are minimum at the fault point and increases towards the neutral. And option D is none of the above. So discuss among yourselves about these 10 MCQs, and then we will see in the comment sections. Drop the answer in the comment sections. Thank you. Thank you so much for the today's lecture. Thank you so much.